I can form molecular orbitals from atomic orbitals by taking linear combinations of atomic orbitals. I can add them and subtract them with constant coefficients. So my atomic orbitals, when I'm talking about the p orbitals, can be added and subtracted. I have to choose an internuclear axis, though. So I'm going to choose the internuclear axis, the axis that contains both nuclei, as the positive z-axis. If I choose the positive z-axis, then I can add the pz orbitals together, pz atomic orbitals, to form a molecular orbital. Now, notice I'm going to add these two orbitals, but look how the signs overlap. Remember, red and green represent opposite signs. Green can be positive, red can be negative. So if this is the positive z-axis, then this orbital has been multiplied by -1, because it has minus along the positive z-axis, while this orbital has positive along the positive z-axis. So I'm going to bring those two together and make that linear combination. I choose that linear combination because that gives me amplitude, a higher probability of finding electrons between the two nuclei. Constructive interference between the two nuclei leads to a bonding orbital. So pz and pz can combine to form a sigma bonding orbital. Of course, you can add them with the opposite sign, and pz and pz can come together where the amplitudes interfere destructively, and I get positive and negative adding to 0 amplitude and giving me a node between the two nuclei, and get an antibonding orbital. I can show you that with these little models. Here comes one atom with a pz orbital and another atom with a pz orbital. Multiply this one by -1 so that I get constructive interference, and I add to form constructive interference between the two nuclei. And I call this a sigma bonding interaction because the electron density is along the internuclear axis. That'll be my definition of sigma orbitals. I'll also get an antibonding orbital when I add them like this, where the positive and negative parts add to give me a node, add to give me 0 somewhere between the two nuclei. Now I can look at the other p orbitals. There's also the px and the py. If I add those, they're above and below that z-axis. So here I can add together px and px and get a bonding orbital. In this case, I'll call it a pi bonding orbital. Pi bonding orbitals and pi antibonding orbitals have their electron density above and below the internuclear axis. So I can get a pi bonding from the x, but I can also get a pi bonding from adding py and py. So 2 pi bonding orbitals, and if I add them with this sign, I'll get pi antibonding orbitals, one from the px and one from the pair of py's. So I'll take 1, 2, 3, 4 atomic orbitals and make 4 pi molecular orbitals, 2 bonding and 2 antibonding. Those are the pi orbitals and sigma orbitals formed from linear combinations of atomic p orbitals.